presenter. All right, so thank you, everybody. Appreciate your attention to the clock and getting back in your seats. There's plenty of refreshments still out, so if you haven't partaken yet, you are certainly encouraged to grab some, get an opportunity. Our next presenter is Bob Sword. I'm gonna let him self-introduce, and he's gonna talk a little more about the demonstration project that we'll see here this afternoon. So, Bob.
Thank you. I'm Bob Sword with VSL or Structural Technologies, and I'll explain a little who that is in a minute. I started with VSL back in 1985, so I've been around a few years. I'll let you do the math. But I'm going to pass around a couple of wedges so you get a sense of the difference between epoxy wedges and a standard wedge. You can see the difference in the teeth. So I'll start that with you, Drew. So what I'm going to go over in my section is really who VSL is, or structural technology is here in the US. Talk a little bit about the checkered past of external tendons. I think we've had a little bit of that today. I think most of you maybe have heard of what it is, but I thought I would just touch on it briefly. Then talk about the unducted external tendons, then get into the Laurel Fork project, and then talk a little bit about going forward. What are some of the things that as we are introducing a new technology into the bridge market, what are some things we need to be doing as we go forward to make sure we're giving, am I doing something wrong?
No, it's just showing your transcript.
Oh,
You're transcribing it.
Yeah.
well, that's it. That's probably.
I didn't want to shut that off because I'll probably also shut off the recording, so. I'll just leave it be. Okay.
Okay, so VSL here in the US. So some of you may have been working with VSL over the years. It began as a part of a Swiss contractor back in the 50s and 60s. It came to the US in 1965 and incorporated in California to take advantage of the post-tension concrete bridge market in California. The VSL stands for Bohr Strand Systems Losinger, if anybody is interested. In 1998, there was a change in ownership at 1992, actually, was VSL was acquired by Bouygues, a French contractor. And then in 1998, we decided to change the legal structure here in the US for VSL and go from a wholly owned subsidiary to a license arrangement. And at that point in time, a license was granted to structural group or structural preservation systems. And now we operate, our legal name is Structural Technologies, but a lot of people know us as VSL, and that's really who we are. Even though there's a change in the legal structure, we still have a very strong connection with VSL International. We have a lot of interaction with them on a lot of different levels. Okay, well, that's not. Well, am I not presenting?
It's stuff.
Is it not presenting or something? It's not slipping. It's not going to the next slide. What have I done?
It's died again.
So just hit that, okay.
Yeah,
Let's do that.
it's died again.
There we go, okay. So a little bit about the checker past of external tendons. There's been some discussion about this, but on Mid-Bay Bridge, there were some tendons that failed due to corrosion, and some of the root causes there were, poor grouting practices and some substandard duct materials. There's a similar issue on the Marina Enon project, similar, tendon failures. They also went back and tried to fill some of the voids that were caused by the bleed grout, and we ended up having a dissimilar material issue also at that location. So there's some things there that promoted the additional corrosion and failure of the tendons. There were some partially grouted tendons, either caused by bleed water or just poor grouting practices. There were some issues with the selection of materials for the external tendons, the HDPE pipe. And as a result, there was the response of the industry was a coordinated effort, really led by ASBE and PTI. And we got involved, the owners, we got engineers involved, suppliers, contractors, really all the stakeholders that were going to be involved with post-tensioning and external tendons. And we developed a multi-pronged approach to dealing with the issue. We realized that grout was probably one of the key issues to deal with, but we didn't just focus on addressing grout. We looked at the whole system from top to bottom, looking at the design of the systems, the anchorage designs, the system design in detail. We looked at the materials that we were using in the post-tensioning systems. We looked at the equipment that was being used. In the 80s and 90s, we used big, large paddle mixers. As we looked at the type of materials, we've shifted over to colloidal mixers. We looked at a lot of the details to make sure we're, providing details that allow for the tendons to be inspected. We require now written procedures for all the different activities that are done. So there's a good method for communicating not only to the crews, but also the inspectors and everybody involved so they know what to expect when they go out to the job site. Training was an area that needed to be addressed. So there's now ASB and PTI, have ongoing training programs that are really being effective. And then documenting quality control. These are all areas that we address. And we published a couple of specifications, M50 and M55, that really provide guidance to the industry on how to do durable post-tensioning. And, how effective has this been? This is one of our superintendents, his primary business is doing inspections and investigating tendons, where he goes out and drills into a tendon, looks for voids, looks for soft grout. And you can see from this graph that the tendons that were installed in the 70s and 80s, and even into the 90s, we were finding issues, but in the tendons, but when we got into the 2000s and beyond, once we began to have a better spec and better understanding of the issues, those issues really started to go away. And there's still a few outliers where we've had some issues, but primarily, we seem to have been able to address, a lot of the issues. So I think that the effort that the industry put into solving these issues has been very effective. So moving on, but even though that's been effective, there's still other ways that we can skin a cat. We don't just have to use grouted tendons. We can look at other solutions, which we're here today to talk about, which is the unducted tendons. This has been done in other types of applications. We've already heard from John and others how it's been used in Japan for quite a while using epoxy strand. VSL is also used, a very similar application in wind towers where we've done used either galvanized and greased and sheathed strand or black and greased and sheathed strand, similar to the type of strand we would use for stay cables. We've even done strengthening projects. We recently did a project in North Carolina? South Carolina, thank you. Where we used a greased and sheathed stay cable quality strand to do an external repair. So this is the technology that's out there. Certainly we're going to talk primarily about epoxy coated strands, which has advantages, but also there are other options out there also as well. You should be considering. And over time, I was talking to Reggie and he was looking for a demonstration project to be able to try and use epoxy strand, external unducted tendons. And so we looked at our jobs that we were working on. Fortunately, we have this project, even though the details were originally designed for grouted tendons, we looked at them and we felt that we had an opportunity there to be able to make some adaptations to be able to accommodate the epoxy strands. And so that's where we're at today with this demonstration project. It's the Laurel Fork Bridge. It's in an amazingly beautiful setting. And so it's not a very large bridge. It's a 3-span bridge, precast segmental, was built balanced cantilever. And Justin's going to show you a lot of the details about how the bridge was built. The end spans are 155 feet with a main span of 255 feet. The tendons we're going to be using as unducted tendons are the external tendons. They're 12-strand tendons, and there's 2 tendons per span, 1 per web wall, for a total of 6 tendons that we're going to be showing you today. Typically, what we would do for an epoxy type tendon was we want to use our standard anchors systems wherever we can. Typically, what we would do is we would upsize the bearing plate. So if we're looking at a 12-strand tendon, we would want to upsize to a 19-strand bearing plate to allow room for the additional area. Because these coated strands are larger diameter, so we need a little bit more space for the tendon to fit into the bearing plate and into the anchors. So we would upsize the bearing plate to accommodate, the more space, and we would use special wedges, which I hope are still being passed around to you guys a chance to see the difference in the teeth on those wedges. Before we felt comfortable doing, providing these tendons on this project, we went through a testing program. That's outlined in FHWA, where we did, single strand static strength tests. Had to achieve 95% of guts or aughts with 2% elongation. This was, and I think, John, actually, you answered a question to me earlier that I've had for a long time. I said, is the compatibility between the wedge teeth and the thickness of the epoxy. I didn't realize that they had thinned it down. So that helps to answer a lot of questions for me. So we went through that testing. We did a single strand test up at CTL. We did a full scale test in our facility in Dallas with 12 strand tendon. Just wanted to make sure there wasn't any anomaly that we weren't catching by doing this single strand test. And then we did the fatigue testing required on a reduced size specimen, which is a 2-strand tendon. We did 500,000 cycle tests with a strain of 60 to 65, 66% of aughts, and then 50 cycle fatigue tests going from 40 to 80. And the specimens performed very well. So on this particular project, because the segments were already cast, we already had our standard anchors in the segments. So our standard 612 bearing plate was cast into the anchor and into the segments. So in the way we had detailed it is we had the tendons coming out straight out to the diaphragms. And then we had a Diablo at the backside, and we had a HDPE pipe sticking out the face of the diaphragm that we would have originally intended to hook onto the external tendons. But we ended up not having to do that with the epoxy strands. Diablos also were used at the low point deviation points. This is the details that we used there. And again, we had HDPE pipe going through the Diablos, which is in line with what you saw earlier on some of the details that John showed. But we had to make some adaptations to the anchor because the bearing plate was not upsized. It was our standard size bearing plate. So what we ended up doing is having to push the wedge plate further away from the anchor, the bearing plate, to allow room for the strands to splay, but not at such an angle, so it wouldn't rub against the inside of the anchor body or the bearing plate. So we designed a custom anchor head. And because we were using epoxy strand, we needed to have, it's very similar detail to what you see on the DSI display. We had to have a way of sealing the backside of the anchor. So when we fill the anchor after stressing and cutting the strands, we don't have whatever we fill it with coming out the backside of the anchor. So we have a compressible filler and then a compression plate behind it. And we have some bolts on the front face that we can use to pull that compression plate in to create the seal back there. Some of the benefits that we see with going with the unducted tendons, and there are probably others that I've probably overlooked, but to me, the first one that really is most important is the strain corrosion protection is applied in the manufacturing process. One of the challenges we face in the strand supplier is that a lot of these segmental jobs, they go on for 2, 3, 4 years, sometimes even more. But we bid them, and then we want to secure our strands so we don't get caught in an escalation or some unforeseen circumstance where our costs go up beyond our control. And being able to apply the corrosion protection, right away, then we have a way of protecting ourselves against, spoilage of the strand over time, so we can acquire the strand early in the project. As we've heard about, the strands are inspectable. We can verify that the corrosion protection system's in place, either through using holiday detectors or other methods. We can look at the tendons themselves. Even in place, we can do some checks to see how the tendons are looking. They're replaceable. Even if you grout the anchors, at the very end, you can remove that grout fairly easily and still be able to replace the tendons. Eliminating the grout and the grouting operation. And there's a lot of issues that we face with segmental bridges, particularly in colder climates where we can't grout because it's too cold, or we can't grout because it's too hot. And we have to, put corrosion inhibitors and things like that in to extend the window. By eliminating the grout, then we've eliminated that complication to the installation. There is some reduction in materials. We don't have to buy the grout, we don't have to buy the HDPE pipe. In my feeling also, this is going to do a lot to rejuvenate the precast segmental span by span construction method, which primarily uses external tendons. So I think that's a great thing to see more precast structures built out there. And the system can also be adapted for internal ground tendons. We've done this with VSL on projects, in other parts of the world. So these tendons can be used internally and grouted. I think that would be an option for potentially splice girders. Right now in Florida, you can't use, splice girders are really difficult because you have all this voids in your web. And you use flexible filler there, so you basically take away your shear section. So being able to grout that void, then it potentially gives you an opportunity to do those structures again. So going forward, how am I doing on time, Greg?
Right.
Okay, going forward, this is the new technology here in the bridge, and for this application, although it's been around for a while, we've seen there's several stay cable bridges that have used the epoxy strand. We've done some repairs with, unducted tendons, but it is a relatively new technology for owners, engineers, and contractors. So I think there needs to be a need for some guidance on how to do it correctly to make sure that owners are getting what they are paying for. So, as chairman at N50, I'm gonna make sure we deal with this in our next, coming meetings. And some of the things that came to my mind is we need to talk about the coating. Not only is, what is the coating? How thick is it? How robust is it? In the state cable specifications, we have certain robustness requirements as far as abrasion resistance and impact resistance and things like that. One of the things that occurs to me, if we want to have some kind of containment system in the event a strand were to fail for whatever reason, either during installation or stressing or some point in time down the future, we would want to go whipping around inside the bridge, potentially hurt somebody if somebody happened to be in the bridge. I think there should be some guidance on what needs to be done to make sure that the anchors are encapsulated. Is there some sort of water tightness we need to have similar to what we have for stay cables? I think we need to have some guidance on vibrations. These cables, especially if they're unducted and individually strands out there, they vibrate between themselves and the whole tendon itself can vibrate. So I think that's something we should provide guidance on also. Also finishing, what needs to be done to finish the tendons. And there's going to be some installation and structuring requirements. I'm sure that Justin's probably going to touch on, and you may have some questions also about. So as you're walking through the bridge, if you see something that you think the committee should be thinking about as we're trying to address this, please let me know. Send me an email, send it to Tim, send it to Greg, either Greg, and we'll make sure it gets incorporated into the discussion. So in summary, external tendons, post-tension tendons, they have had a checker pass. I think the industry responded and the results have been very effective, in my opinion. There are alternatives to grouted tendons, which is the external unducted tendons, which we've been talking about. And there are some significant benefits to these unducted tendons. And we do need some specifications, some guidance for owners and engineers and contractors to make sure we're putting these structures in correctly. So that's what I have to say right now. Does anybody have any questions? I went fairly fast, I feel like.
Can you go back one slide? So if I don't want to increase the size of my blister and I want to stay with my 19 strand trumpet and I don't want to upsize it to a 27 strand trumpet, can I use that can that you showed right there? Or is that just a one-off?
You could probably do something. This is a one-off. This is a custom anchor we did because we were retrofitting into an existing, but it certainly can be done. We're doing it here.
Pretty slick.
Yeah. Yeah. And we originally started off with a two-piece, like a tension ring or a ring, and then also the standard anchor head. And then we said, let's just make it one piece so it's not too many pieces up there trying to manage. And I think that was the right move. Yes, sir.
Go back one or two slides, you had a bullet there that said, tendon finishing, what does that mean?
Tendon finishing is, basically, cutting the tails off, capping it, injecting it. Is there anything else that needs to be done, that I hadn't thought about? Surely you guys can stump me.
Is there a slated time for release for the new M50?
Right now, and Tim, you can jump in if you want, but I think right now we're about to issue a new version, Is it ready to go right now?
Well, we had an addendum recently related to other matters, but with the cycle that's going for M50.3, it's supposed to culminate in 2026.
Yeah. So it may not more likely it will not make it into 26, but it doesn't stop us from issuing an errata or a technical note or other things in which we may want to do before another 8 years goes by. Yeah. Yes, sir.
So I know when we were installing these, we had a temperature restriction, I think it was 19 degrees for stressing. Maybe John speaks to this, but is there an upper limit on that? I mean, you had limitations with grouting, but for stressing this, we didn't want to hold for stretching if there.
There was a limitation on temperature when you were stressing the epoxy strands
On the cold side.
on the cold side.
No upper limit in terms of like ambient temperature conditions.
But he's saying if it got too cold, they couldn't stress.
Right.
Minimum 14. There's going to be 14 degrees Fahrenheit.
Fair.
But why is that?
So epoxy coating getting hotter under the constant pressure. So they got
14 degrees Fahrenheit.
You know, basically, Japanese based on Japanese specification. So that's definitely cold. That's for safety.
It's 14 degrees Fahrenheit, right? So was that the limitation? Was there something different?
I could be wrong.
It's 14 Fahrenheit, and only because we've only tested down to that point in terms of its ductility.
Okay.
We didn't find a failure below that. We just haven't continued down.
Okay. Well, I don't want to be stressing at 14 degrees. I could see it happening in Minnesota. They still love it cold. Was there another question out here? We can go up higher than that. We'll just have to do a custom anchorage. So we can go larger. I think we can go up to 55.6.
Yep.
Pretty big. I'm okay with that though. Anybody else? There's gotta be one more question out here. Come on, William. What else? What other question we have? Sure.
Is there any concern in the field that the workers are gonna get these mixed up? Wedges?
You know, there's always a concern when you have two different types of wedges on a job site. So I think, one of the things that happens with these external tendons, that's typically when the bridge has been built and the closures are all in place. So it might be possible that, the other wedges are removed, but there is a risk. Because from the outside, they don't look any different until you look at the teeth. So there is always a risk there.
You could make them look different. Absolutely. You can paint them blue.
Yeah, you can do something on the back. It's, you get a bucket of these things in the hunters. So it's, I think it's favorite thing. Go ahead.
That's similar issue with the ram, because the wedges in the ram have to be the same type of wedge, correct?
Correct. And that thing, Justin's gonna touch a little bit about that, because we have, over here on the table, we have a set of grippers that we use for the epoxy strand. It's different than our standard grippers that we use in a jack. It's to allow the epoxy to, flow in the teeth. Oh, good.
I was gonna say in the field, we had 2-piece wedges for the bare strand and 3-piece for the epoxy, so.
Okay.
Yeah, that's a good idea.
There you go. Good. Thanks.
So Bob, if you want another question, I'll throw you a softball. John said that the install price was probably going to be less with this. You as a post engineer that have installed miles and miles.
I'll show you the cost report.
I mean, this versus wax, I mean, is this a less risk?
From a wax, I think the wax or this is probably, I would say this is preferable to the wax. But our field guys love the wax. They go home and they're not all dusty. They're not tired. They haven't had butt bags all day long. So they like, not having the new grout. So the field guys, if we can eliminate grout, they're happy.
Okay.
Yes, sir.
Going back to the wedges, is there a reason choosing a 3-piece versus a 2-piece for the epoxy necessarily?
That's a good question. These wedges were developed by VSL. Actually, we got them from a job that they're working on in India. So we basically worked with their wedges. We didn't design or develop our own personal wedges here. So this was the wedge that they had developed there. I could certainly ask them why.
They more commonly use the 3-part as well.
Right. Drew, do you have a question?
No, I said we all want to bridge the 3-part, but that's just.
So any other questions? Yes, sir.
Is there a concern with epoxy strand of rebiting the strand in the same spot and breaking it like there is on bare strand?
Did you hear that, John? Is there a concern about rebiting over the existing bites?
Yeah, I think there would be no difference with risk and bear.
Yeah.
I
Would there be any chance that the epoxy is out of the way now and the teeth would get further into the strand?
think it still remains, I mean, it still maintains its height in between every tooth.
Okay,
I think also just to elaborate on that, on the job site, we took an epoxy coated strand, we ground off the epoxy just to see the teeth marks on the wires. And they're much less significant than on a bare black strand. So I would say that there's probably not any further risk to double biting on the epoxy coated strand.
okay. Absolutely. Yeah, there's a lot more travel, so you're gonna have a lot more wedge speed loss, both, yeah. And Justin, I think is gonna touch on it. Talks. Anybody else? Got me one more question. Anything else?
Thank you.
So I have been reminded that industry is actually working on, with, in conjunction with Federal Highway, we are working on a tech note and a special provision to cover this material. One of the DOTs we met with early on was excited, but said, how do we incorporate this into a construction project? What are the specifications that we would use? So the industry is working on that, sort of more to come. So let's move now to Justin's presentation. If I can. Oh. All right, it's yours.
Perfect. I'm so glad Greg's doing all this IT work. Totally looks. Yeah, so Justin Campbell, I work with BSL, had done since 1996. Been fortunate to travel to many large scale projects. Very fortunate to be here in the US and present. Of course, I'm not from here, as you could probably tell. I've lived in Texas for 8 years. Accent hasn't changed. Originally still from Scotland, I guess. That's about the only word I can really use. So originally from Scotland. But yes, enjoying my time here in the US. Oh. So of course, as an operational individual, always have to have a safety moment. We've not had one today. Maybe that's something to think about in the future. But as a safety moment, I'll throw it out there if anybody has a safety. What I would say is that we're going to be coming home around 4 o'clock, 5 o'clock. These roads, according to what I know around here in North Carolina, deer, wildlife, run across the roads, right? So just be aware, be alert, particularly as it gets closer to sunset. Around these windy roads, please be extremely careful. I've had it many, many times where a deer has run in front of us. Anybody else? I'll throw one out if anybody else wants to say something. Okay. So of course, as we've all heard this morning, it's a 3-span bridge. Precast segmental, 56 precast segments. The maximum weighted segment was 131 kips. And the height variance is from 13 feet to 8 feet. We had to, obviously erect our heaviest segment, at 310 to 320 feet away from a radius perspective. So we had to pick a 120 kip segment and place it 310 to 320 feet away. To be able to do that, that's a huge radius. And you'll see that more in perspective on site. But this drone that's taking this picture is extremely high in the air to try and get it all in view. But as we walk on site, just think about where this crane was parked and where that segment is going to end up. It's hugely impressive. We've spoken about the bridge a little bit. Mr. Bob has had some post-tensioning pictures up here. We have the two tendons in span 1, we have two tendons in span 3, around about 155 feet. And there's one deviation point in these tendons in segment number 9. So you will be able to see that when we're walking around on the job site. And as you can see here, just in the red, that's the deviation point. Then on span 2, there's 2 deviation points. So we've got a 240-foot tendon, and we've got 2 deviation points at segment 9s. As you can see, just around at the bottom. So this is what it's going to look like to some degree. Now we've got the 2 epoxy strand tendons in there. So just as a point to note, if you're not comfortable in confined spaces, maybe don't put yourself in those confined areas, right? As you enter the bridge deck, it is going to be a little bit crunched over for the taller folks. For the likes of us, we'll be okay. But yes, it will be a little bit crunched in to get in through the doghouse, through the diaphragm, and then we'll walk down to the pier, and bear in mind that pier's 13-foot segment, so you'll have plenty of space to walk up there. We're going to walk around the bridge deck as well. There's going to be various groups. So a group can go up on the bridge deck, a group can go down onto the ground and down to where that crane pad was. So there is a bit of hiking to do down a ramp. David from Benoit has kindly volunteered to hike up and down the groups. It is a bit of a trek. So again, if you don't feel comfortable trekking it, think about it. It's a live job site. But we are more or less shutting down most works around 1:30, 2 o'clock when we arrive. But it's still a job site. There's still trips and falls and other things to think about. So just be aware of your surroundings. So from an operational perspective, we have this project to do. It was originally intended to have a grouted post-tensioning external system. Now we are going to use the epoxy coated strands in the demonstration project. We know we had 6 tendons to do, not a lot. There's not come up with huge elaborate ideas. There's 6 tendons to install. So we have to keep that in mind, of course. The deviator, the diaphragms, all cast. The anchorages were all in there. So we had to take that into account, of course. So our epoxy coated strand systems, which Mr. Bob had shown, were specifically designed to suit this already cast system. We wanted to use our VSL equipment. We didn't want to go out and buy new jacks. So we have modified our equipment, and I'll show you a picture of that in a minute. And we'll talk about the modifications on those pieces of equipment. And then the installation method. I know that in Japan, they typically would do full prefabrication of these tendons and then ship them to the job sites. We didn't really have that option here. So we had to do an alternate installation method, which we'll touch on slightly again here. And so taking that all into account, as Mr. Bob said, we designed our anchor. We tested the anchor. We made sure our concepts worked. As Mr. Bob's also highlighted, it evolved from a 2-part anchor into a single-part anchor for easy handling, take it into account. And you can kind of see a little bit here. There's the back plate. The black section here is the closed cell nail, foam nail prim. And then the front of the anchor, the bolts will come through, squeeze this plate up, and that will close against the strands. It's sufficient shore goes against the shape of the strand. And then as you can see in this picture, that's the back end of this anchor. You won't see that on site because they're all installed. But there is some of the protection caps that are not installed, so you can at least see the front of these anchors. And now we touch on neck welding. We wanted to use our existing jack, which is a ZP460. We use that typically on our 612 systems. But what would we have to change? Well, as Mr. Bob hinted at, we have to change the gripper wedges. So that was one aspect. But those gripper wedges are bigger. So we have to change, obviously, the gripper plate and everything that goes with the back end to grip onto the strands. Now, at the front of the jack, nothing internally changes in the jack, but at the front of the jack, as somebody had pointed out in one of the questions about the wedge seat. Yes, the wedge seat is different. So we had on the demonstration project, in fact, we had to do some investigation on that first tendon. And we learned some things from that first tendon in that the recessed depth, how much would we need on that recessed depth to allow the wedges to come out at the anchor head and to sit back in properly at the anchor head. And what we did was, in order to investigate that, was we made our recess for the front of the jack slightly bigger than what it maybe could have been, should have been. And then we had shim plates on the inside. So we stressed our first tendon. We took some experience from that first tendon, and then we put the shim plates in if we needed to modify the depth. And in fact, we needed to modify that depth by a 1/4 inch by 6 millimeter compared to what we had thought theoretically. And we ended up around a 17 millimeter, nearly 3/4 inch recessed depth compared to on a typical black strand where it might be about a 1/4 inch. So quite significantly different. So the installation process, we'll be able to talk a lot more about this on site as well as we do our tour. I'll just brush through maybe some of these things that you may not see today because of course they're installed. But as John had previously highlighted, the strands came on wooden reels. So we had to pay off individually each strand from a wooden reel. And then of course, you don't want it dragging along the ground. So we had to make some little stands. And in this case, of course, you could protect it from using carpet. Right? You could protect it using plastic. You could protect it from the ground using other things. We decided to use little wooden stools, I guess, because those wooden stools we could also fabricate for inside the bridge deck too. And you'll see that in just a second. Here's the wooden stools on the inside too. And then during the installation process, we decided we're not going to use a strand pusher. We've got 6 tendons. We're not going to prefabricate the tendon. We're just going to push these by hand. They're 155 feet long, or the maximum was 241. So not huge tendons, bit of muscle power, and it would go in reasonably well, which in the end worked. But there is some challenges with that, which we might see in just a second too. Then the most important thing at this point in time for us was the layering of the strands. So of course, if we want a replaceable system, we can't have like a black strand, which all the strands will be crossed over each other as they push. You're pushing the tendon, strands are diving under each other, going over each other, and you end up with a bundle. Here we wanted to layer these strands so that if you did need to replace the tendon, you can detension each strand individually and replace these strands. And you are allowed a twist, now remind me, 30 feet. You're allowed to rotate throughout the bundle, right? So long as the layers stay the same. 30 feet twist. Okay. But anyway, the layer definitely had to be maintained. And there will be some samples up there where you will see the little layering tools that were used, provided by Sumidin, and also the shape adapter, which is right here to maintain the 612 shape. And with that 612 shape, we can run that shape adapter along the tendon, tape the strand bundle. You'll still see the tapes on site to maintain the shape. And then of course, now you're looking at the wedge. So if you're going to layer it, you also need to know which strand hole you've put in which strand. So each strand was numbered. Each anchor hole in the anchor head was numbered. So you knew where strand number 1 was, and strand number 1 would follow from one end through the 155 feet and come out the other end at strand hole number 1 on the other side. So now you know exactly where all your strands are, which again, from a detensioning perspective, makes life a little bit easier when you're using the hydraulic jacks. And of course, like I just said, maintaining the bundle, maintaining the shape. We've taped them more or less every 9 feet-ish, 10 feet. You'll see tape along the tendon length. And then our hand installation speed. Although it might not be super fast, but again, it was only 6 tendons. But we did have some challenges. As you can see, these guys are trying to push through this diaphragm. This would not happen if everything was upsized. Right? If we had gone from a 612 to a 6-9, we want to use 12 strands in a 19-strand system, you wouldn't have these challenges coming through diaphragms. You wouldn't have these challenges going through deviators. Of course, we didn't have that in this demonstration, so we did have some challenges to get strand through the ducts at these points. The challenges in ducts could be from a little kink in the shape from the precaster. Of course, that caused significant challenges on 2 particular tendons. Or it could be just a deformation in shape. Could be maybe just a little bit of epoxy inside. Because when you see, I think on site we'll have a cut sample of a 612 duct, and you'll see 12 strands in there. There's virtually no other space to accommodate any deformations. It was super tight. So again, just to touch back on that stressing equipment, using our existing PT normal equipment. Our normal equipment is a 4-inch stroke jack. If you're considering that in that 4-inch stroke jack, you have, let's say 3/4 of an inch maybe to pull up force during restrokes. So now you've used up 3/4 of your stroke. And now you're also using up 3/4 of your 3/4 of an inch as the reset during strokes. So now you're about 1.5 to 2 inches of lost pull, because you've got the pull out and the reset back in. So with a 4-inch stroke jack, that means every time you stroke, all you're maybe taking is 2 inches, which means a little bit more additional steps, a little bit more additional time to get to the force that you want. In future, that could be accommodated by different jacks, different strokes, of course. But at this time, we didn't have the time to make it for this demonstration project. So successes. Just going to touch on a little bit of successes and a little bit of challenges. From a success perspective, 6 tendons are in, which you will see. 6 tendons are stressed, which you will see. So far, I would say that the whole demonstration has been a success. There's a lot of learning, information from that, which we'll need to document and record and prepare for the next time. This is the second unducted system that we have done in the last maybe 6 months. We did South Carolina a few months ago, and now this one. So the unducted tendon process seems like it's definitely a viable option. Working with Sumidin has been an interesting experience. Luther has been on site throughout the process, and without Luther's help, we wouldn't be standing here today looking at 6 tendons, maybe 1 or 2. So yes, working with Luther has been definitely helpful. Sumidin have been super with information. So method statements from Japan, processes from Japan that we can review and look at what we can integrate here in the US has definitely been a benefit. Their past experiences. Installation by hand, well, we've proven it can work. So that is a viable option for short left tendons. Obviously additional care, additional efforts, maybe some additional efforts that come from the experiences of doing it the first time can also be taken into account the next time. I would say, obviously John had shown a slide about the limits of the epoxy coating coverage. I think if we're using this in a post-tensioning application, we should definitely be on the upper echelons of that range, primarily to allow for rubbing together any contact with something. It's going to happen. We're on a construction site. So it does happen, and with the larger thicknesses on the epoxy coated strands, if you're on the upper range, it'll give you that ability to maybe survive that or to implement a repair. Repair procedures were workable on site. I think Luther's also going to do a demonstration later today on that repair and then what can be used to test that repair. And then overall, the stressing operation after the first tendon experiences, it went relatively well. Then, of course, we always like to look at the challenges. These are the things we're going to remember. The good things we find it hard to remember, right? But we always remember the difficult parts. But the tight ducts, yes, by upsizing, as Mr. Bob alluded to, upsizing the ducts, if you want a 12-strand system, I think it'd definitely be better to go with a 19-strand duct or a 19-strand anchor. It just makes life so much easier to be able to push these or pull or whatever process is going to be used for installing these epoxy coated strands. Segment joint misalignments, precast segments. I mean, we shouldn't kid ourselves, right? The precasters are good and fantastic at doing what they do, but you've got to accommodate for some misalignment that's going to happen. Rubbing of epoxy coated strands together, side by side. Again, by having the thicker coatings that we had at Laurel Fork, we were very fortunate to have that upper echelon range, so that was good. Repair procedures and the availability of that, we actually reached out to try and find some repair material. It took about 3 months. That was the lead time. Fortunately, Luther had some. So that was very fortunate at the time. Anchor protection, constraints, and then of course the stressing operation itself, the time to perform. If we want to include or use existing equipments, it might be a little bit longer in the process just to do that. But as you can see, this sample is actually on site and there's no space for a misaligned duct, bit of epoxy inside, a kink somewhere. There's no space inside that duct for anything else. And just some thoughts that came whilst we were doing this process, specifications, guides of good practice like PTI have or as they have. The development of those is essential. So again, as Mr. Bob said, if you walk around and you see something and you're asking a question and you think it'd be good to include in such a good guidance report, or that question needs to be answered to be included in that report, I think that would be very useful to share. Vibration of tendons. I know that in one of our inducted a few months ago, we put some clamps for potential vibrations. It's maybe just something to think about in inducted systems, the vibration of those strands and tendons. Don't be afraid to, when you're walking along the bridge, give the tendon a knock, hand on it and feel the vibration, just for experience. Containment for what if scenarios. So of course in the bonded system, if a strand fails, it's in the duct. If a strand fails in this, it's out in the open in your segmental box. So maybe something to think about, a containment for a what if scenario. We're always supposed to consider what ifs. Diablo and deviator blocks, we covered that a little bit this morning, which I didn't know you were doing, so that's great. Larger bell openings, different shapes, maybe something to consider for a non-inducted system. Diaphragms and deviator blocks. Although, let's say 99% of the tendon is inspectable, right, and you can see it. There's always a patch through the diaphragms, or there's always a patch through the deviators that you cannot see. Maybe something to think about. And then inspections over service life. You know, what are these inspections to be? What equipment has to be used? That would be also interesting to have in maybe like a guided practice, guided good practice. Just a cool picture of a second getting tilted. Any questions and answers? Yeah, yes, sir.
The material for your anchor heads, for your bridge frame.
For that, we just use steel. That was a machined steel piece.
Okay, and are those encapsulated or protected somehow against corrosion?
Good question. I don't have a picture of it, but you'll see it on site. There's a encapsulating protection cap, which will encase it all. It'll cover the whole anchor head. Yes, sir. And then that will get filled.
So I think, I'm under the understanding when you do the holiday detection with the spark detector, you have to ground one end of the strand to create a circuit, right? So if your anchor head is completely encapsulated, what's the, how do you attach to create that circuit so that you can do the?
So you need to take a indirect grounding, so like a wrap tendon with a steel plate, something to take a indirect ground instead of a direct ground.
Would you be able to ground it to the bearing plate? Connect the bearing plate?
Yeah, of course. Of course, yeah, you can take a direct grounding, but you need a rotor cable.
Did you guys have a power seer on your mobile parent jack?
We did not. We do not have a power seater in general on our multi-strand system. So that particular jack does not have a power seater on it. Yes, sir.
On the installation inside the box, when you got to the deviations, it looked like there was a sleeve around it. Was that for installation or is that retained in the permanent structure?
So it might not have been very clear on Mr. Bob's slide. The Diablo that we use, so we've got our anchor head, and then we had some HDPE pipe coming through, and then the Diablo was over to create the bell shape of that. So that HDPE pipe that you'll see at the deviators or at the diaphragms at the abutment segments, there's still that HDPE pipe there. And the intention of that was, of course, that for the bonded system, our HDPE pipe would be welded back to that little sticking out part. Yes, so it's nothing to do with the epoxy coating, it's just that to weld.
Inherent to the previous system.
Yes. Yes, sir.
Wonder if you saw any evidence of when the grippers grip the strand and released and grip the strand and released, would the epoxy flake off? And would you have an issue where it could potentially gum up the grippers over time if you repeated use?
We didn't see any flaking of that epoxy coated strands during the gripping, and there's probably some strand tails that you will be able to see on the job site too, to get a feel for how deep that is, how rough it is. But there was no flaking as such. There was no flaking. Yes. The wedges would just bite all the way through, and then the restroke, it would just come through again, no flaking, and it would just rebite again. Nothing in the teeth of the wedge. Yes, sir.
How much anchor set losses do you get for the epoxy strand compared to a bare strand?
The epoxy coated strands, we were looking at 3/4 inch, if I'm right, Chris, right? About there, thereabouts, in reality, for actual. And then for the normal strand, we're looking at, what?
3/8.
3/8. Yes, sir.
I assume we'll see it on the job site, but I'm trying to envision, we're going through this effort to create a pattern of the strand, but when you're running it through a Diablo, how much compression and sort of flattening of that strand root do you see, and does that create issues? I'm thinking particularly at the anchorage, you want to come into the anchor head pretty clean.
I think John had a good slide. Sorry,
I was wondering, I was gonna ask the same question. Will it crush out the epoxy on the strand? You got all the pressure smashing the little bit of epoxy, but it's the surface it's bearing on.
I think it's a good question. I think,
The research you see.
yes,
Yeah, that was the testing that we did, that very question. Proving that it doesn't fully penetrate the epoxy.
you saw the flat, I think in one of John's pictures, you saw the flattening out of the epoxy. But it did not penetrate the epoxy down to the black strand or the bare strand, yes.
I was kind of more curious about the flattening of the bundle shape.
Of the bundle shape. And I think also in one of your section slides as well, you showed the tendon up or down on the ducts. Yes, you're going to get some of that, but not to such a degree where it can't be replaced. It will still be pre-tensional replacement.
So in regards to replacement, is it your intention that you could replace one or two strands of the 12 strands, or you got to replace the whole 12 strand tendon at some point if you decided to do that in the future?
I think, so in a cable stay system, you can replace strand by strand because they're not being deviated. I think in a deviated system, I think the probability is you'd have to take out all 12 strands.
Structures, pier diaphragms or through the deviators. Where we have a Diablo that's a form void, right, and then maybe it's stripped away and leaves a concrete face. Would you recommend that those have to be sleeved with HDPE pipes as a softener to the epoxy?
Personally, I've used it on a couple of projects, this exact type of Diablo, and not had the removable types. I've done the removable types as well. I much prefer this continuous duct coming through any concrete, and then therefore the strands are softened, as you say. It's not in contact with anything that could cause a problem. You agree, Jeff?
Yeah, we'll talk about that in a minute.
Good. Good leading question. Yes, sir. There's no fiber optic on this one. No, sir.
So the Japanese technique for installing was to pre-bundle the strands in the factory ahead of time and bring them out. So do you go through the same level of effort to keep the strands as parallel as possible in that scenario? Like, I'm just wondering why we went to such a huge effort this project.
So whenever, strand trace or crossing during installation, so it may tendon configuration may change during stressing. So it's causes strand grabbing each other. So to prevent this, so you need to all strand completely parallel to avoid the configuration change.
Okay, so when you pre-bundle them and you're still maintaining that parallel orientation for all the strands.
Yeah, basically, the hex frame is, sitting somewhere outside the gutter. So all the rings go through the hex shape. It takes every 10 meters, 10 foot, 3 meters to keep the all strand parallel.
Is it your intention to ship pre-bundled, pre-cut tendons rather than just sell the strand in the US?
Yes, this is kind of, we like trying to.
I'll talk about that in a minute.
Right.
I'm just gonna comment on the thickness, we're hitting on that, so the thickness range that, for example, we supplied to this job was about 24 to 35 mils. So plus or minus 5 mils is the tolerance that we're able to hold that. The specification allows 15 to 45. So we put a thickness range in there that, to Justin's point, gives us some room for something to be, partially damaged during installation without dropping below the minimum to 15 mils. But we also have to keep into consideration the bite-through wedge design to be compatible with the range of thicknesses we're going to provide. So that's an important conversation we would have with the post-tensioner, is, you know, what the wedge system is to the thickness range that we would hold in supplying. So it's different than the ASTM thickness range, but it would be something that would be a specific arrangement for the project. That would be designed to be compatible with the wedges.
What would the maximum mill thickness be that it's consistent with the wedges? Is that within that?
That range is not even recommended. Just described, so it's like 24, 35 range, and that's what we supply. We could go lower, you just, at some point, when you go too high, then you've got too much epoxy you're trying to bite through, and then you don't get good penetration to the skin. And so that's the main consideration, is making sure your thickness is compatible with it.
So if you just went by ASTM and had the 45 mil, the way must nearly bite very well, it would feel
Right, but you have to have, that ASTM spec is just for any epoxy application anywhere. If we're doing a bite through wedge system, they're looking at an arrangement, it's supposed to on the things.
So for example, for stay cable, tension is much lower than external tension, but so like a 40%, 50%. In this case, if the thickness too thick, like a 40 or 45 mils, his may not bite. So that's the process. So normally, we are trying to control the thickness lower of stay cables. We are adjusting.
With the tight fit and the bundle inside the duct, did you have any issues with elongations, and did you do an in-place friction test?
We did in-place friction test. We did our elongations. Our elongations came out good. Came out within the expected theoretical ranges that were calculated. Yeah, it was okay. Yeah, even with such a tight situation.
All right, thank you.
Perfect, thank you. If I've missed anything that's running through your brain, don't hesitate to give us a shout. I'll be inside the box when we get to the job site, so I'll be able to walk you through as well, maybe some questions there.
But also, we're working on with FHWA special provisions for external tenants. Some of these comments about like wedge and compatibility thickness, they're included there. So there's a guidance document that's underway to address these things, so that it's not just, I said it here and knows, what happens after that.
All right, so we have about 40 minutes. Do you want to do?
I'll do both of them. Yeah, I'll do the.
Which one do you want?
Yeah, that's the first. For second. Back to the. Sit down. Yeah. It's good. That's good. Is that a meal? It's just like 3 hours. Oh, no, that's. Well, it's good that being sport. I'm playing by. This one's extra. Teams. Some way out there.
It's this one. Okay. All right, so with that, Jerry Funkner is going to be our next presenter, and I'll let you come up to the podium and address the group.
Good morning. Obviously, there's a lot of interest out here, so I'm very excited to present what we've been doing here for the last couple of years on this project. I'm Jerry Funkner. I'm the technical director with COE North America out of our Tallahassee office. Quickly, our project stakeholders. So, of course, the owner is FHWA, Eastern Federal Lands Highway Division. The EOR is Eastern Federal Lands Highway Division. So I took over as EOR of the precast segmental bridge and the substructure. That's part of the little construction change that we had during the project. So I really want to acknowledge that, the project itself was developed by Eastern Federal Lands Highway Division engineers and the original precast segmental bridge and then the minor modification I made actually, turned to be into the engineer of record for the structure. Our contractor is, Structural Technologies and Vanoy Construction. And, we are, Cody North America also serves as the construction engineer. Quickly, main span 255, we got the, but you've seen the number of decks, so I'll kind of blow through this slide, allow for some more time. This site had a lot of restrictions. You're gonna see that out there today. Wetlands, project boundaries, it's in a very environmentally sensitive area that we were working in, so the access issues and the big crane that as you saw earlier, that is all due to a lot of challenges that we had out there. Even the bats were out there making things difficult for us, disturbing their homeland. So we had to really minimize all those effects. And what you saw there was the existing bridge. And I'll just quickly show when we brought that thing down, what that looked like. Sorry to the bats for their loss of their home, but had to happen to get this project to go through here. The design modifications. Actually, we did a sister project to this, I-26 in the Blue Ridge Parkway with Structural Technologies prior to this. And so we actually adapted the forming system to be able to utilize this on this project. So those two little highlighted areas of purple and yellow, that's the extent of the changes that we made to adapt that form to this project. And so we were able to do that. And then the precast, the pier columns were actually set to be precast. And so we changed those to reinforced concrete, cast in place. Very difficult to take two twin columns and then have a precast cap piece on the top of them to make that all fit. So we did that to make it a little more adaptable and but kept the overall shape and all those things. And then one thing we didn't realize that would be very good for this project was actually changing the steel bent pipes to Diablos, which became very good for this, what we're talking about here today, to be able to adapt this project for use of having epoxy coated strands. Many things could be reused from I-26, so especially with the same techniques, same bridge, same everything that we had within there to be able to be adapted and utilized by Structural Technologies. So part of this is the modification that we made to turn me in the EOR. So this project actually is a demonstration project to every single person out here except for me. I'm the engineer of record. I'm the one that's going to, in the end, going to be responsible for the use of the epoxy coated strand on this project. And but these are some of the adaptations that we had within there, so we're able to accommodate the existing form to come into this shape. Quickly on the superstructure, so you've seen before, this is a haunch girder, precast balance cantilever. It's pretty vanilla as far as those aspects of it. You can see the tendon layouts for the side spans and the mid spans. We have internal bonded tendons for our cantilever tendons, and then the majority of the post tensioning provided is from bonded internal tendons, that's the continuity tendons at the end spans and mid span region. This project actually is an excellent one to be able to be used as a demonstration project. We only have the single epoxy coated strand that was, for the external continuities that are in each span. Our ratio of the external tendons that are unbonded to the bonded is quite low. So in the end, from a design point of view, to meet the ultimate requirements that we had in both the positive moment regions and the main span and the end spans, we were able to accommodate that with using the effective stress of the external tendons alone. And so that made it to where the choice of this was, fairly easy from that point of view as a designer, but using this new material. Zooming in was great, but also with support to COE as well, came into our offices and gave us a presentation of much of what you saw here today. And with the on-site support, we also have, we're working in Florida where we have fully unbonded systems. So a lot of research has been done on fatigue testing of unbonded tendons that we were able to utilize as well to be comfortable with the exchange of this system from one for the other. And in particular, the details that you see out there today. But I do want to acknowledge that the bridge was designed for, ducted systems that we have for the original, grouted external tendons. And so structural technologies, like I mentioned, had to do a lot of adapting to be able to make this work, to get this system within details that were not originally designed for this post-tensioning system type. So here are some results. As a designer, what changes do we have from the external system to the epoxy coated to your typical? So here are the results of the first 4 tendons that we have. We utilized the same friction values we're using standard HDPE, the DR17 pipe that we would have for your typical system. That actually worked out to be able to create the sleeve that we would need. We didn't want to have those strands rubbing against the concrete that we had from the Diablos that were that spun nylon type. And so that worked out very well to have that in place to be able to utilize it. And once again, the change to the Diablos was very fortuitous to be able to have those available to be able to utilize that with this post-tensioning system. Elongations end up being very good. What we didn't know was what the live end anchor set was going to be, 3/4 to 7/8 of an inch. So we were actually on the phone with David Dry. I was doing the on Teams call. He had his camera set up. I was watching stressing from Tallahassee as they were doing it, because we wanted to know exactly what those elongations and the anchor sets were to be able to evaluate those tendons. It's a stunning video, David, but it's not going to make an Oscar. But we did realize that we had a big difference than what we had from our original assumption. So we were able to crank out those numbers. Alejandra here is the one that actually ran all the design calculations, analysis models. So she's here with those and crank those out. So we were able to quickly update the elongations and all those targets to be able to adjust that to what we would need on site. Interestingly enough, the dead end anchor set only ended up being pretty standard, 2/16 to 1/4 of an inch, but they were preceded, with a pipe sleeve to get those, engaged. I've got another presentation. We'll talk a little bit more about some of those stressing issues on site as well. But from a design point of view, that was really the primary change from what we have from a stress point of view. And then once again, we simplified the ultimate calculation by just using FSE for confirmation. The substructure, you can see here, the pier columns were really adaptable to be able to go to a reinforced concrete, precasting 2 piers, and setting up those operations for this was really not cost effective for structural technologies in Minoan construction to be able to do that way. So the post-tensioning layout, actually, again, the original details from Eastern Federal Edge Highway Division were utilized, so we did not change any of the post-tensioning part of our work. And having the tangent length within the pier segments actually, again, turned out to be a great detail, because we were able to confine the free length of the tendon we've been talking about between the Diablos on both spaces. And so we have that. And we were able to not have the fatigue or any issues with that go back to the actual wedges where we were anchoring these new epoxy coated strands. One thing I will say, we do have the vibration requirements. You look at the ASHTO code, you'll see every 50 feet, we're supposed to have a support for our external tendons. For years, nobody's done that because it's not an issue. And so if you grab a grouted external tendon in a segmental box girder, you shake it, it's not going to move very much at all, even with the standard lengths that we have for routine bridge construction. But when you go out here this afternoon, be sure to shake one of those tendons, because you're going to see that the non-composite action of the individual strands working together, they will vibrate with some amount of stimulus from your hand. So that's definitely something we'll be looking at, and the M50 committee can look at addressing that as well. So for our construction sequence, this is what we assumed in the beginning, as with good segmental bridges. Many times we'll change the closure sequence, things like that. We did here. And so we did adapt those changes, completing the side spans first, and then the mid span as the last closure. I believe we still have the closure beams still on.
Yes.
Yeah, so they're out there, and that's the last one that we closed up just a couple of weeks ago that we finished up here. So for those of you not fully familiar with precast segmental construction, so the way it works is that we start off with temporary props or temporary support. And so will see those out there on site here today. And we support the initial pier table, we'll call it, your pier segment, and then your one up, one down, supported on the temporary frame. We actually don't have the bearing, the permanent bearing grouted, so that we're only supporting on the first four legs for our cantilever stability. Let me continue. We erect segments one up, one down, and stress the cantilever tendon in between to be able to make them continuous with the cantilever. There's epoxy glue in between each one of these segments so that we initially squeeze that out to have just a very thin portion of epoxy in between each individual segment. And then the cantilever tendons are threaded through and then grouted as well. End span units are completed. We have a strong back beam system that we put across the joint to help assist us with closing up the geometry alignment and then holding that steady as we're casting the closure segment across, and then followed up by stressing all of the continuity post tension that you see there. And then here is actually where we're at today that you're going to see out there on site. We've got the last closure was made a couple of weeks ago. We have the closure beams are still on site. Geometry overall has been very good on the project. You'll see a nice, smooth, good looking bridge out there this afternoon. And then we are in the process of just finishing up that last main span, those external tendons, but everything else has been stressed up. As you saw before, we have the erection by crane, erection by big crane, to be able to have the site limitations that we had on site. We had a very minimal area where we had access, and so this large DMAG was brought out on site to be able to access the entire job and erect these segments from that one location. The sand pit that you see there on the left-hand side, that's where we actually had to bring the segments in, and then we rotated them, larger ones that could accommodate transportation right there on site. So it's a little convenient trip we've used for quite a number of jobs. The in-span false work, again, to minimize our effect on the valley below. So we only have one post, and then we actually just erected the bottom segment in the middle, and then we did a little mini cantilever, just supporting them by that initial false work system for that center one, and then we just cantilever right on top of the false work versus having a whole bunch of posts and jacks that we need to have within there. This view, you can see we have stability towers. We actually use concrete piles, which is a little bit different. At the time, this was when COVID was going on, and we had all kinds of material constraints and supply issues and things like that. And so Structural Technologies was able to procure these as a means of getting materials out there on site that were readily available at the time.
Vice versa, Danny. We intended to use concrete piles, couldn't get our hands on them.
That's right.
And then we ended up on steel.
Part of this utilizing the previous project within here. So there's other revolutions on this job. It's actually been constructed using BIM. And so we have a full parametric design approach, made very easy to be able to adapt one bridge to the other, utilizing the Grasshopper and Excel to be able to replicate the geometry within this project using our graphical means to be able to auto-generate files. If you have any questions about all that, you can ask Alejandra right here. She can tell you all about it. Also, this software system actually was able to be very adaptable as we went through the construction stages, make those changes like the closure sequence changes. We reran the elongations in no time to be able to modify the epoxy tendons, things like that. So this is the wave of the future that we've been incorporating on this project here today. In the end, we have, even though it wasn't a project requirement, we had a full BIM model by taking all of this information that was generated, auto-generated with the Grasshopper system. And then what you see there on the right-hand side is full 3D model. You can highlight, shadow all those information, and all the reinforcing, all the design parameters are all available right there within this individual BIM model. And we were able to actually auto-generate all of the CAD and production work systems as well. segmental bridges are highly adaptable from the industrialization process to be able to utilize this. So this is one of the benefits of precast segmental construction, to be able to rapidly generate all of this information all the way down to the geometry control. It all comes from and flows with this methodology through the same pathways and processes to be able to generate that all down to the geometry spreadsheets that you see there to the right that we utilize to be able to monitor the construction processes. So Greg, I'm gonna go ahead and switch to the next one. Spend a little more time for that.
I have a question here.
Yes.
Where's the light moved out? Where's the light moved out?
There's an access roadway, which you'll see a little bit again today if you go down to the bottom. And on that roadway, that's what we talked about, and then put it down there as well.
It says, looks like it's late at top of the hill.
Okay.
It's that.
Here, yeah.
Yeah, it's this.
Yep.
Oops. Did this.
You should be good. Okay, so I was on site about 2 weeks ago when they were starting to install these tendons, and of course, this EOR, make sure that I understood what was happening out there as well, to be able to do my duty and chunk, sign, and seal this thing. So I learned a lot that day. I've seen a lot of tendon stress over the last 30 years, and so this was an interesting. Okay. So as mentioned earlier, so structural technologies went through the approach of utilizing more standard, anchors, part of it because they had to, well, the procedures that we use in US practices. So we didn't have the ability to get, hand delivered bundles of strands, manufactured like they were mentioning in Japan. And so they adapted to the site that we have and the constraints that we have with the US practice. So there was no white glove approach of bringing that in. So a lot of that and working with Simadin to be able to bring in these strands and deliver them. With that, we'll talk a little bit about that. One thing we learned is that the wedge seating. So the initial jack was set up with the nose plate for bare strand tendons, and so there was an adaptation that had to be made. When we pulled the first ones, it actually having that longer length. The epoxy, was we've talked about the tapered end of the wedges themselves, but they actually dragged onto the strand, and so they would actually pull with it. From what we can understand on that first tendon, and then so that had to be modified to reduce the amount of travel that they had within that nose plate. We didn't have that issue with bare strand. And so there, the first tendon had a couple of the wedges where the relative position of the wedges came out of sync, and we had to make some adjustments to those guys. So really is what Justin was talking about earlier. So Structural Tech has the phenomenal nose plate thickness was 22 millimeters, and then they had wedge shim plates that they had installed. So we adapted them on site to be able to reduce what he was talking about is the height between the face of the plate and then where the wedges would actually, when they draw back in from one pole to the other, it would restrict the travel of those wedges from that relative to that, and then turned out that 16 millimeter was a good number on site. Obviously, we can look at the prayer, but it worked for all of the remaining tendons, and it's been successful in doing all those perfectly. As you've seen earlier, we have the epoxy coated wedges are different. They've got deeper teeth. They're also about 1/4 of an inch longer than the standard wedges that you see. One thing we'll note earlier, VSL does a two-part wedge system for your permanent ones, but many manufacturers use a three-part. So there's one part, one area where you could mix up a strand or the wedges from the different strands. So the number of pieces is not gonna be all the time a good indicator. But you'll see the epoxy coated wedges, be sure and look at those. They are a very, much more robust system to be able to grip it. And I've got some photos later about some where we remove some of the epoxy to verify it. You'll see some strand tails out there on site. So this is what the wedge anchor marks look like. One thing you'll notice as you look at the strand tail, so when we go to 20%, you can see at the very end, the indentation of the wedges into the epoxy is not nearly what it is as you go down to where we were more at our full stressing force. So there is a variation in the depth, but the epoxy is strong enough, obviously, to be able to hold and secure. You'll notice as we've looked at, I've looked at a bunch of strand tails. There's no slippage that you see within there. So the epoxy works very well to be able to grip the strands, even at lower stress levels, to be able to pull. And some of the discussion about whether it got stripped and things like that or damaged, really, we didn't see a whole lot of that out there. And you can look at those on your own, the strand tails. These are the pulling head wedge marks. You'll notice those. That's grease that is applied there to be able to allow them to slide a little bit better within the pulling head. So after stressing, we pulled some strand tails. One of the things we wanted to do, obviously, with this new epoxy coated system, we wanted to verify that we actually had the wedges gripping into the material. Simon also brought out a little bit thicker range on the epoxy from the what's covering over the crown versus the minimum that you see within the ASTM. And so we actually pulled some of the epoxy. You can see there that we have both the pulling head wedges on the top, and then you can see the anchor head wedges on the bottom. And you can see where the 6 wires that encompass the, around them, all of them have indentations from the wedges pulled from that, even with the thicker epoxy crown thickness that we had and utilized here on site here. So we're able to achieve the grip that we want to be able to make sure we were embedded into the strand, the steel portion of the strand for that engagement. So the minimum thickness, 0.38 millimeters. Again, Simon was out there on site of the field. They were great for working with structural technologies. They were also great for me as well to verify that, with their experiences that they had in Japan and all that, where, and how the installation was going in here. I learned a lot about actually, what they were doing. And especially relative to the practice that we had with here on site. I will say that the hardware that was provided, because of the original design was probably the most challenging conditions that you would have. As Justin mentioned earlier, having the bigger anchorages and larger Diablos would be something that would provide you the ability to install this with a little bit more simplicity and not shoving things through, but being able to guide the strand through. So the epoxy can be manufactured from 0.45 to 1.1 millimeter thickness in the end. In talking with Luther, he was helping out that they actually selected wire with more like 0.6, 0.8 millimeter thickness. And so that was understanding that they would be pushing in the installation with not having strand by strand in a supplied bundle that was already prefabricated in a factory and brought out to the site. So acknowledging that. And in the end, with the field installation, Luther was out there. He had the ability to measure the crown thickness that was residual after the strand was pushed in, and verified that we were indeed greater than the ASTO, the ASTM minimum. And so that the coating, although you will see some abrasion out there. So take a look at the strands. When you see them, you'll see the crowns where they're not, perfectly, pinched. You can see where there was rub as they were installing them and what that looks like. But you'll see a little bit of minor abrasion. I think it was mentioned earlier when there was a nick. You see there's obviously a nick versus just normal abrasion on the strand. So as you walk up and down, take a look at the strands and you can see how they look from an installation method from pushing. Here's what one looks like. So we had this is a fully, stress, strand, obviously, and so, having the strands parallel, obviously, I think is a benefit. It's actually, I'm gonna say necessary to be able to, get the strands installed. If you think about it, when you push a strand through a solid duct that we have for a normal external tendon that's ducted, you're actually controlling where the strands go. So they're all confined within that bundle and they're laying on top of each other. And so the relative length and position, they're not draping between supports like you would for these unducted systems. And so having them in a bundle actually assists with the place and position these ones so that we don't have one twisting versus the other. We end up with a different length of strand and that free length between the anchorage. Within there, I didn't inspect all of the tendons, and I think the maximum we had one tendon that had like a quarter turn over the entire length of the tendon, very minor, and certainly within as Luther mentioned that they over in Japan they have quite a bit more twist than that, and so we were easily within that, and you can look at the epoxy, coating. You can see a little bit, like I said, some surface issues and few things every now and then where repair was necessary. That I'll talk about here in a few minutes. When we get to the live end, we have quite a bit of anchor set, as I mentioned earlier, and so you can see by you look at the heads, you can see where the wedges are fully seated into the recess of the wedge plate that were custom built for these the wedges and the installation that we had here on the project. And even on the dead end where we had quite a bit of difference in the anchor set versus the live end. If you look at those, they're all also fully seated into the wedge head.
So they preceded them.
Just put the pipe, Captain, put the pipe.
Okay.
This is that one when we had the unequal, there's a little bit of drag, where some of the epoxy was where the wedges were moving, relatively too deep within there, and so we had a little bit of that on that very, very first one. So you've already seen that. I didn't mention that we did use the standard, for HDPE pipe, the friction values that were 0.17. So that all worked out. And then the elongations, as Justin mentioned, were very good. A little long as you would expect for a straight tendon profile type of a tendon. So strand installation. This is, Structural Technologies utilize a series of these supports. They all have pipe sleeves so that they can, when they were draping the strand and pushing them through along there, they would not rub on some fixed piece. They were able to have those PVC sleeves to be able to minimize the any friction that they had within there. Now, one thing you're going to note is that you look at the length of the supports, and you can see that little bit of drape of the strand I was talking about earlier. So that's kind of important to make sure that when we have these tendons stressed up, that we have that uniform bundle and that the individual length of the strand is same relatively between the two anchors, so that when we start stressing, we're pulling on an equal length instead of just having one strand shorter than the other in between that free length. And then we have a reduced number of strands actually being engaged at the beginning of stressing. So these are
Was there consideration for pulling each individual strand, some nominal, 1,000 pounds or something?
well, with deviated tendons, we have deviations at both of the anchors and also the deviation point. So you'll have some strands that are at the top and then they're at the bottom, will be bearing against the concrete. So you really could do an individual strand pull like you could for a cable stay. So that's one thing, when we think about these as having unbonded, unducted, it's not like the cable stay where you have a vertical inclination in each individual strand is, by itself, if you will. But with the deviations, you still have where the strand is actually pushing up against the, where it's bearing. And so with these, the idea of utilizing these for continuous external tendons, you're gonna have deviation points bottom, bottom, top, bottom of the bundle, so that the replaceability and also the stressing of an individual strand really isn't practical because of the bindings you're gonna get. It's good for the bundle. Yeah.
It's even a challenge on a straight tendon too. So, in South Carolina, we did the first unducted, application. We had the core through there and yes, the tendons were straight, but those cores weren't perfectly level. And just that minor amount of deviation there was enough to bind up the tendons.
Well, that roadway geometry, if you have a bridge and a side curve or a crest curve, you're gonna have all that in there. Those issues are all gonna be in there, so, recognizing, that and being careful about the placement. So when you push strand, you lay it in there individually, as they laid it in there, and then, I think the inspection piece was mentioned earlier, so as they lay one strand in there and you have it in final position, that's your time where Luther was out there looking at all those strands and, to be able to inspect those. So even though you can't see the interior of the bundle when it's fully together, you can, as they place an individual strand, you can observe what it looks like.
So I question that, Jerry. I mean, in the pre-tension application, we preload every strand to 4,000 pounds or something, and then we gang stress the whole 70 strands at one time in a massive frame, and we pull all the slack out, and it helps us a lot. I understand you're saying that when you pull the slack out of the first one, you're gonna be rubbing on the top on one location, the bottom on the other location, and messing up the strand group. It seems like Suman's done a good job of trying to keep everybody oriented, and with some nominal force, 1,000 pounds, 2,000, it's not gonna be enough to cause a lateral force to crush that piece of plastic. I mean, to me, it seems like this sagging thing you're worried about or worrying us about between these frames is a real problem, or it could be a real problem with somebody sloppy.
After watching them install it, my opinion is that once you lay these things in, if we found some way to secure a simple sleeve along the length of the tendon, if you stress one strand, it's almost like a stay cable. We can go ahead and get it to the profile very close. And then we can take all the sag right on out of there, just like we do in a normal ducted system. So that's one of the suggestions I, have in the back of my mind that could be done, be very easily.
Stress one strand.
Stress one strand or a couple strands like.
I feel better with one strand, with no strands.
Or even with partial, and then we could get these things all within the same relative geometry very easily. And then we can maybe eliminate a little bit of this, shoring up we got to put in there.
Sure.
Yes.
If you keep the strand bundle, I mean, you're keeping all the strands the same length. We multi-strand tendons, we take the 20%, take the slack out.
Yeah.
Then you take them up and we make you an issue out of this, right? I mean, if the cables are all bundled and they're all the same together, then there's not a whole lot of variety, like between the strands.
Well, like I said, the difference, you guys are very careful in being able to put these supports within here, and then we have a normal duct, we don't have the ability to strand or lay. And if someone was not as.
Yeah, I'm just wondering about stressing one strand and still putting strands in and trying to put it.
No, the whole thing.
Whole thing.
The whole thing, and then you have it all together, then you can, you can put your compactors and all that, put one in there, yeah, yep. So, obviously, we're learning. So, with this, it's just great for everybody to go out there and see it. Seeing is believing a lot of what you heard, and then you'll be able to have this within there. So something like this is the strand compactors. I think you probably have a couple of them still out there, but they were used to be able to control along with the tape, reinforced tape that was utilized to be able to keep them relatively in the same position. Here we had, obviously with the equipment that they had, the old plates, we had to adapt to the sleeve and help get and push those through. So, as Justin mentioned, having proper sized hardware is going to be critical to that as well. One thing that you don't notice is that with regular bare strand is that it comes out nice and straight when you get done. But there is a residual curvature when you pull off epoxy coated strand. It's got, and you can, the photo here doesn't really do it justice to be able to have that, but it's not where like a bare strand comes out. So it's a little bit installation, pushing through those, tight quarters like, Justin was mentioning, it makes it a little bit more challenging just from a strand. And then increases the, maybe the amount of abrasion that you get out there as well. This is some of what you're gonna see, the little abrasion of the crowds. Take a look at that. As, mentioned, they had to, push it through the existing hardware that they had. I think it was, very smart for Simonton to bring out a little extra thickness for us to be able to have and make sure that we had what we needed. I think that's something we'll again have to discuss in future conversations as to what would be appropriate for us to still get the bite marks that we need and also accommodate, and possibly, thinking about US practices. And where they were just utilizing some paint marks on the strands, make sure they were relatively equal as they pushed them all through and through the ducting system. And then again, this, anchor head, from my point of view, obviously they sized it up. Structural Technologies designed this thing and they incorporate a lot of the details, as was mentioned earlier, to be able to compress, that seal inside of this rubber anchor head. And then, so this gives us the replaceability. You can cut the strand on the opposite side. This entire thing comes off with the grout. And so this would make a tendon very easily replaceable in the future with the Diablo and details that we have out there in the span to accommodate that. Here's a view on the inside so you can see where the cheese plate, if you will, behind that is the rubber seal that we have. And so those 3 bolts that we have on both faces, they'll just crank those up once it's installed, and then it seals onto the epoxy coated strand, and then they'll be sealed up for the grouting operation. And then again, they had to use, the PE pipe that was already there for the previous details. As discussed, we need to have bigger pipe to work with the strand, not only because of the strand diameter, but also to be able to install this a little bit better, where we could possibly limit the amount of abrasion as we have to push through the details that were not, developed for this kind of a system. Same thing on the deviators. You'll see that all out there today. When you go out, be sure to look at, if you're not familiar with Diablos, take a good look at those, and then you can understand a little bit of the concept. It's easy to see on a screen, but when you actually touch and feel it, it becomes a little more real to you. And then we did, we had a question earlier about repair. And so you can actually splay the wires apart, the strands. And then, right there on site, Pat Sluther was, produced a repair right there. And I watched him do it. It was less than an hour. And from identification to the point where he actually got the materials out and then was able to, use the heat gun. It was a cold day that day. I could vouch for it. And he, was able to, put that on there and then by isolating that particular location on the strand and then perform the repair right there. And then it was heated up afterwards and then cured, well before we actually stressed the tendon.
Jerry, you said that he actually splayed it apart. To do that repair?
Yeah, and that wood stick that you can see, there on the.
It's like a wedge on it in there just to get access.
What was it, a spoon?
Yeah. I bought that.
That is a special tool.
It's simple.
Yeah,
So we have a couple minutes for questions for Jerry, so.
no, before.
So Jerry, you talked about your analysis earlier about bonded versus unbonded ratio in this bridge. In a bridge that was designed from the very beginning with more unbonded tendons than we have here. Is this gonna give us an advantage now? Are we gonna be able to take advantage in the analysis phase and save some cost?
Well, that's gonna come in the whole mixed reinforcing, that's a topic that's come up and there's a FIB committee 215 that I'm actually co-convener on to help develop design procedures for utilizing, mixed, reinforcement where you have unbonded, bonded tendons and reinforcement, and then determining, what we could get for capacity. But unbonded tendons, they are not strain compatible with the cross section, whereas bonded reinforcing and post tensioning is. And so that's a big to do about the level of actual increase in force that we get or stress within these tendons as we go through, to get to ultimate, but actual strain that we get in these external systems. So we're working on that. There's going to be some revisions over the next few months starting to come out. Current AASHTO does not address this fully, other than a paragraph that says you should do a compatibility analysis based on deflection of the system and all of that. But we're hoping to come up with some new provisions. That's in the works way. Anything else? Yes.
Has the grit impregnated epoxy been used in an internal application to confirm it does bond and can use strain compatibility? If you were to grout it?
I'll defer to my.
Yeah, we do, pull-out testing between the grit impregnated and bare strand. The grit impregnated is slightly better than a bare strand in terms of bond capacity.
Has it been used in any application in a bonded acid?
California and Lake Ridge.
That's a lot of application. It's been down around for decades. Yeah. You had a question?
Yeah, did you do a lot of mock-ups or have the contractor doing test boards or test things before they did done the full productions?
We did not. So we built the first one, and that was really the test case to be able to do this demonstration.
We did the field scale test.
Yeah.
Demonstration.
The whole.
Demonstration.
The only the epoxy coated, just the replacement of that. And with it being, we didn't really have a concern because with it being replaceable, if the first one didn't work out, we just cut it out and do whatever we did. So that, right, call it, it's a true demonstration and installation. So, and the tendon itself was not pertinent to the, the erection, sequencing and all that. We could easily, continue on with construction with the tendon in or out. So it really, like I said, this was a great project to be able to use as a demonstration because we had a lot of flexibility as far as assessments. Yes.
So this project actually is a combined usage of bonded and non-bonded.
That's correct. That's correct. Unbonded and bonded.
Is it possible to replace more bonded with the non-bonded?
It certainly is. There are many advantages to utilizing external tendons, like reducing web thickness, things like that. And so, in many applications, so there's this, I think this system has some real possibilities, especially with the way the stressing has gone. It's gone very well and it's met every, the requirements that we've had so far, so.
All right, one more question.
Are you using, did you use a lower stressing value? So instead of 80%, 70 or 72 or 75?
We were actually limited at the beginning to the acreage limitations to get, no more than 70% at each anchor head. So we were about 75%. Yep.
All right, thank you, Jerry. And if you have more questions for him, you certainly can visit with him afterwards. And so just a couple of things I want to clarify. One is a lot of the installation challenges, I don't know if you picked up on it from the team, but a lot of the installation challenges really dealt with because we changed a job sort of on the fly from a bare strand to epoxy coated strand. So some of those things in terms of upsizing ducts and whatnot were not possible. So it did create some challenges, but the team kind of knew that going in. The other thing I want to clarify is for this project, Federal Lands Highway Division is actually the engineer for the National Park Service. So the National Park Service is ultimately the owner of the project. So with that, I'm gonna make sure we're no longer. We're stopping the recording. Okay, so this is all stuff.